Let's start this session by talking about the importance of dimensional analysis. We're going to have a thought experiment first to make things crystal clear. So, as you can see on the left-hand side photo on your screens, you have a cylinder that is placed right in the middle of a flow that is moving in this direction, right, or this direction. If I ask you to find drag force, you already know that the drag force is going to be in this direction. It's called F sub D. And as we discussed before, drag force is as a result of pressure variations in front of and behind this cylinder. Now, if someone asks you that how you can find out all the variables that a drag force is a function of, most of you would probably say diameter of the cylinder is important. Yes, so this would be the diameter of the cylinder that is right across the flow of water, or it could be flow of any other fluid. So diameter is one of the variables that drag force is a function of. What else though? Diameter is obvious because as the diameter gets larger and larger, obviously drag force is going to get larger and larger, right? The other thing is velocity, right? The velocity of fluid that is approaching the cylinder. And it's easy to understand why. If you are in a car and you put your hand out of the window and you are driving 20 miles per hour, the drag force that your hand experiences is going to be way different than the drag force that your hand would experience if you were driving 80 miles per hour, right? So velocity is another variable that drag force is a function of, and I'm going to write it over here, velocity. What else? You would probably tell me that fluid properties, right? Density of the fluid. So imagine air and imagine engine oil. The drag force for air, when your fluid is air, is going to be way smaller than the drag force as a result of engine oil, right? So I'm going to write density, which is a property of the fluid, and also viscosity too. So these are the variables that we know that drag force is a function of. Now, imagine that you're working for a company, and the company asks you to find a relationship between drag force and different diameters of the cylinder, or different velocities of the flow, or different densities from different fluids. So what you're going to do is to set an experiment, right? And when you have that experiment, you are going to do probably something like this. So you are going to create graphs. On the y-axis, you will have drag force, or FD, and on x-axis, you will have diameter, D, right? And you are going to generate some graphs, some lines for different velocities. So I'm going to say these are different lines for different velocities. Starts from velocity 1, and you're going to try different velocities. Let's say that you are going to try 10 velocities, so I'm going to say V10. And also, you're going to try different diameters as well, right? So you're going to try 10 diameters, diameter 1, 2, 3, 4, all the way to diameter 10. So in other words, you will get 10 points over here, 1, 2, 3, all the way to point 10. So in order to generate this graph that tells you different diameters versus different velocities, you need to do this experiment for 10 times, right? Because, so for diameter 1, you're going to repeat the experiment for velocity 1, velocity 2, velocity 3, 4, all the way to velocity 10. So this will have, this part will be 10 experiment. And because you have 10 diameters, 10 times 10 would be 100 experiments just to generate this graph. And then you realize that, okay, so this graph is only for one specific density and one specific viscosity, right? But the company asked you to try different viscosities and different densities as well. So what you do is change the density and change the viscosity 10 times as well. How does that work? So you are going to create other graphs for all different, the graph would be the same thing, but you're going to try, first of all, 10 different densities when viscosity is constant, and get the graphs again like this. And again, this is velocity 1 all the way to velocity 10. And again, you get D1 all the way to D10, the same thing, right? And then you are going to do the same thing over here, but this time, this is D, this is FD. So you're going to keep the density the same. Oops, density should be rho you're going to keep the density the same, but change the viscosity 10 times, right? And also this should be 1 over here. There we go. Okay. Again, you would get lines over here from velocity 1 to velocity 10, and diameter 1 to diameter 10. Similarly over here, F sub d, d, this would be for density trial 10 and viscosity trial 10. You get different lines for different velocities and different diameters, right? So you're going to create a matrix of graphs. And how many graphs in total it would be? It would be 100 graphs. Because you have 10 different densities and 10 different viscosities. And each pair of density viscosity will give you one graph, right? So overall, you will have 100 graphs, right? And remember that here, I told you that for each graph, you will do 100 experiments, right? So you have 100 experiments times 100 graphs. It would be 10,000 experiments, right? Now, let's do a little bit of simple math. Let's say that each experiment takes about half an hour. So then we have this 10,000 times half an hour. Then we know that to do all these experiments, it takes 5,000 hours. And 5,000 hours divided by 8 hours per day, divided by 8 hours per day, it would be 625 days. So it takes you 625 days to complete all these experiments. So you do all of these stuff, you will create a very long report, and you take that report to the company that you're working with, and you ask them that, hey, I did all of these experiments, and it took me almost 2 years to do all of these experiments, and here are my results, 100 graphs. I have done this for 10 different densities, 10 different viscosities, 10 different diameters, and 10 different velocities. And this is how drag force changes with diameter for all of these experiments. And then your boss asks you that, hey, did you do the experiment for diameter 1.251 feet, for example? And then you look at all your documents and you say, yes, it's in page 225. And then he or she asks, did you do the experiment for diameter 3 feet? And then you say, oh, no, I didn't do that. And then your boss tells you that, hey, the other guy or the other lady that I gave him or her the same assignment gave me only one sheet of paper, and they told me that all what I wanted is included in that one graph and one sheet of paper. How come you have 100 graphs and still you haven't done the experiment for the diameter that we want? And then the reason for that is probably they did not take fluid mechanics, and they did not talk about dimensional analysis. So using dimensional analysis, we are going to make sure that we don't need to do 10,000 experiments to generate results that we want to. We are going to do some dimensional analysis to reduce the number of experiments that we are going to do, to reduce the time that we are going to spend on it, and most importantly, reduce the amount of money that we are going to spend on these 10,000 experiments, right? So now we're going to talk about how we can use dimensional analysis to reduce the number of experiments. All right, now you're out of the office of your boss and you are devastated. You have spent 2 years of your life doing some experiments and you just learned that you haven't done it correctly. And you are also interested to know how the other team has done the experiment correctly, and also they have just did it on one sheet of paper and they have created only one graph. So you head towards the other team and ask them, hey, how did you do the experiment, and how did you come up only with one graph that summarizes the entire 10,000 experiments in one graph? They're going to tell you that they took fluid mechanics with Professor Nassab, and Professor Nassab taught them how to do this. So they're going to tell you that we used 2 different non-dimensional numbers. One is Reynolds number, and you're familiar with Reynolds number right now. Reynolds number can be written as rho v d divided by mu. So rho is the density, v is velocity, d is diameter, and mu is dynamic viscosity. And remember that these variables are also in the variables that you had in your experiments as well, right? And they said, because we wanted to find drag force, we were looking for another non-dimensional parameter that gives us the drag force. And if you remember, when we were talking about drag, I introduced you to one coefficient called drag coefficient. And if you remember, drag coefficient was drag force, or F sub d, divided by rho, velocity to the power 2, diameter to the power 2. Perfect. They told you that they created a graph like this. On the x-axis, they had Reynolds number, rho v d divided by mu. And on y-axis, they had drag coefficient. All right, then they started to have different combination of things. So they started with one diameter, one velocity, one density, and one viscosity. And they got points like this. Perfect. And then they only changed diameter to from half a foot to one foot. So d2, they kept everything else the same. And they ended up getting points like this. Then they said, well, maybe we should change the velocity as well. Then they kept everything else the same and changed the velocity. Changed the velocity only. And then again, they got some points like this. They were like, wait a minute, no matter what we do, all these points fall over a single line like this. We discovered something. And yes, sure they did. They used a method called dimensional analysis, using two different non-dimensional numbers, Reynolds number and drag coefficient, to develop only one curve that can be applied to any diameter, any velocity, any density, or any viscosity. Notice that they did not do the experiment for 10 diameters or 10 velocities or 10 densities or 10 viscosities. They only did 3 experiments, and they developed this curve that can be applied to all other different experiments as well. So because of this, they could save a lot of money, they could save a lot of time, they could save a lot of engineering help, and so on and so forth. So this is the power of dimensional analysis, to save you valuable time and money. Now, you have one reasonable question in your mind right now. How do we find the non-dimensional numbers? So how to find non-dimensional numbers. So what we're going to talk about right now is how to find these non-dimensional numbers and how to show you different problems can be associated with different non-dimensional numbers. I'm going to teach you some ways to be able to find these numbers. Your book has several ways to do that. We are going to focus on one specific methodology that we're going to talk about starting from next slide. All right, the methodology that will help you to find important dimensionless parameters is called Pi Theorem, originally Buckingham Pi Theorem. Again, I'm going to summarize it over here. So this methodology is going to assist you in finding important dimensionless parameters that help you to characterize the problem that you are facing. What I'm going to go over right now is simply the steps and the procedure that you need to take for the analysis in order to find these dimensionless parameters. So number one, or step number one, has 3 sub-steps, A, B, C. First of all, define the physical variables. So we need to specify the n variables that affect the flow phenomena. So we already know that, we already wrote the function, and we know that Fd, drag force, is a function of diameter, velocity, density, and dynamic viscosity. So this is based on your engineering judgment, right? So point A says specify the n variables that affect the flow phenomena. So how many variables do we have right now over here? We have 1 is our drag force, 2, 3, 4, and 5. So based on this, n is equal to 5. Note that there is a line in red. It says do not include variables that are defined in terms of other through multiplication or division. What does that mean? So for example, we know that flow rate is equal to area times velocity. Should you include flow rate in the list of variables? No. Why? Because flow rate is equal to area times velocity, and velocity is already included. So do not include variables that can be calculated in terms of multiplication and division of other variables. All right. Then step B says determine the number m of primary dimensions, and primary dimensions are mass, length, and time, right? So in order to do that, you need to find the dimensions of different physical variables that you defined. You can use table F1 to find the dimensions of different fluid mechanics variable, or you can work it out by the equations that represent them. Some of them are pretty easy. So for example, I'm going to start from D, diameter. The dimension for diameter is length, right? L. And remember that dimensions are inside brackets, square brackets. Next is velocity. What would be the dimensions for velocity? It would be length divided by time, right? Next is density. Density would be mass divided by length to the power 3. Next would be viscosity. You can work it out based on Newton's law of viscosity, or if you're like me and you know it by heart, or you can take a look at table F.1. It would be mass divided by length times time. And finally, Fd, or drag force, you can work it out based on Newton's second law of motion, F equals n times A. So it would be mass times length divided by t to the power 2. All right, so these are all the dimensions for n variables in our flow phenomena. Now, step B says determine number m of primary dimensions. So primary dimensions are MLT. How many of these are inside the variables that we have selected? L is present, M is present, and T is also present. So these set of variables that we have selected, they have all three primary dimensions. So I'm going to conclude that because they have all of them, M is equal to 3. Perfect. And the final step is tells you that this will result in n minus m pi terms that can be formulated to describe the phenomenon. So pi terms over here, the number of pi terms basically, number of pi terms will tell you the number of dimensionless variables. All right, so we know that based on step 3, we have the number of pi terms, the number of pi's is equal to n minus m. So we have 5 total variables minus 3 primary variables. It would be 2. So we're going to have 2 dimensionless variables or parameters. All right, so we know that we're going to have 2. How to find them would be under step number 2. So remember that you're going through a procedure. This was step number 1. To find these parameters, we're going to go to step number 2. Step number 2, select the repeating variables. All right, so let's continue reading. From the list of n variables, and n is 5. So from the list of 5 variables that you have over here, select m of them, and m is 3. So we need to select 3 of them so that these 3 variables, m again, collectively contain all m dimensions, all 3 dimensions. What are the 3 dimensions? Mass, length, and time. All right, so we are going to select three variables that collectively contain all three primary dimensions MLT. So I'm going to select D, V, and rho. Why? Let me tell you. Do you see L, length, at least one time in these three variables? Yes, as a matter of fact, I see it in all of them. D has L, V has L, and rho has L in it as well. Do you see M at least once in these three selected variables? Yes, I see M, mass, and density, rho. Perfect. Do you see T, time, at least once in these three variables? Yes, I see time and velocity. So perfect, I have it all. So the only thing that you need to do in this step is to select M of the variables that collectively contain all the primary dimensions MLT. And I selected D, V, and rho. I could, instead of rho, I could select mu, or basically viscosity, right? Because still I have M, I have L, and I have T at least once in those three too. But it depends on you which variables you want to go with. So there are multiple pathways to go with. The only thing that you need to pay attention is that do not select the dependent variable. What does that mean? Remember that I told you that FD is a function of D, V, rho, and mu, right? FD over here is your dependent variable. So in this step, do not select the dependent variable, FD. Do not select. You're free to select whatever you want to as long as it satisfies this criteria over here. The only limitation that you have is selecting dependent variable. So the three selected variables that I have had are D, V, and rho. In previous step number 2, we selected repeating variables, and I have written repeating variables over here for you, rho, V, and D in our example. Now, the rest of the variables that are not selected are called remaining variables, and I have written remaining variables in our example over here. So now let's get on with step number 3. From the remaining list of variables that are written in purple, select any of them and multiply it by the repeating variables. Okay, I'm going to select for now dynamic viscosity and multiply it by all of the repeating variables. In other words, I'm going to say density times velocity times d times repeating variable is mu. B, raise each of the repeating variables to an unknown exponent, for example, a, b, c, d, whatever, but keep the remaining variable to the first power. So I'm going to say this is going to be to the power a, to the power b, and to the power c, but this one is going to be to the power 1, so I'm not going to change it. This represents the first pi term. All right, so this is going to be the first pi term. What was the pi term? The pi term is supposed to represent a non-dimensional, a dimensionless number that helps you to explore your problem, to explain your problem, to characterize your problem. And then D says that continue the process of selecting any other remaining variable. So what I'm going to do is going to select the other remaining variable that I have and multiply it by other selected variables. So it would be again rho times V times D times FD. Again, to the power A, to the power B, to the power C, and this would be my pi 2. And remember that from step number 1, number of pi was 2, right? So I have 2 pi's over here. So in this step, as you can see over here, we defined our pi terms, and pi terms are those dimensionless terms, parameters, variables that are going to help us to characterize the flow phenomena that we are interested in. Once we have pi terms from step number 3, we are going to perform dimensional analysis and find the unknown powers A, B, and C. So to do that, you can start from the equations that you got from step number 3. I'm going to start with the equation for pi 2, term 2. It is rho to the power A, velocity to the power B, diameter to the power C, times drag force. Now, instead of rho, v, d, and fd, I'm going to insert their dimensions. So remember that it's called dimensional analysis. So I'm going to replace dimensions of these into the equation. Dimension of rho is mass divided by length to the power 3, and the entire thing is to the power a. Dimensions of velocity is easy. It is length divided by time. The entire fraction is to the power b, and dimension of d is l, and the entire thing is to the power c. And then finally, the dimensions of F force is m L divided by t to the power 2. All right, so remember that we are doing dimensional analysis for a pi term, and a pi term is a dimensionless parameter, right? A dimensionless parameter does not have any dimension. So if I want to write a pi term in terms of MLT, it would be m to the power 0, L to the power 0, and t to the power 0, right? Because pi is a dimensionless parameter. So what I'm going to do is change the right-hand side of the equation and write it in terms of m, L, and t, primary dimension. So the left-hand side will remain the same, m to the power 0, L to the power 0, and t to the power 0. The right-hand side will change. So I'm going to write m, and doing algebra, find its power. It would be a plus 1. How did I find that? So here is the a, m to the power a, and there's one more m over here. So it would be m to the power a plus 1. Next one is L. L, or length, would be to the power negative 3, doing algebra, negative 3a plus b plus c plus 1. And finally, it would be t to the power negative b minus 2. Now you know what I'm getting at. So the power of mass, length, and time on both sides of the equation should be exactly equal. So this term should be equal to this term. In other words, a plus 1 should be equal to 0, and as a result of that, a is equal to negative 1. This power, the power of length, on the right-hand side of the equation should be equal to the power of L to the left-hand side of the equation. So I'm going to write that negative 3a plus b plus c plus 1 should be equal to 0. I have a value for a, but I don't have a value for b or c. That's okay. I'm going to move to the third one. This value should be equal to 0 as well. So negative b minus 2 should be 0, which tells me that b is equal to negative 2. If I put a and b in the equation in purple, then I can find c to be equal to negative 2. All right, I found a, b, and c. Now let's take a, b, and c and put it in the equation for pi 2, our pi term, right? So our pi 2 would be equal to rho to the power a, and a is negative 1, times v to the power b, and b is negative 2. What else? D to the power c, and c is negative 2 as well, and eventually fd. Right? So organizing this equation, it would be fd over rho, velocity to the power 2, d to the power 2. This equation for pi 2 is very familiar to you, right? This equation is simply the drag coefficient, right? The dimensionless drag coefficient. So based on dimensional analysis, we found that one of the non-dimensional, dimensionless parameters that is important in the analysis of drag force is drag coefficient. Now, always, it is a very, very good practice to check to see if the dimensions cancel each other out. What do I mean by that? So I'm going to write the dimensions for this to check if my dimensional analysis is correct or not. The units for force was ml divided by t to the power 2. The units for rho was m over l to the power 3. The units for velocity would be l over t, but to the power 2, so it would be l2 t2. And the units for diameter would be l to the power 2, right? All right, so if you take a look at this, they cancel each other out. How? So this would be, this and this will be canceled out by this L and these three L's, right? And then this t to the power 2 is canceled out by this t to the power 2, and this m is canceled out by this m. So our calculations correct, and drag force, or this number, is the first dimensionless number or parameter that is used in the analysis of drag force over around cylinders. Now, this was only for pi sub 2, right? I'm going to do the exact same thing for pi sub 1 to find the second pi term, or find the second dimensionless important parameter that is used in the drag force phenomena. Same game for pi 1. So I'm going to write down dimensions for pi 1. So pi 1 is a dimensionless number, m to the power 0, l to the power 0, and t to the power 0, right? It should be equal to, so I'm talking about this pi 1 over here. Dimensions of rho be m divided by l to the power 3, everything to the power a. Velocity would be length divided by time to the power b. Diameter is L to the power C, and then the dimensions of mu, or dynamic viscosity, is M over L times T. Does not need a bracket because it's not to the power of anything. All right, so again, I'm going to do the same algebra and write this in terms of M, L, and T. So it would be M to the power A plus 1, L to the power negative 3, a plus b plus c minus 1, and then t to the power negative b minus 1. This side, m to the power 0, l to the power 0, and t to the power 0. So this gives a plus 1 equals 0, negative b minus 1 equals 0, and negative 3a plus b plus c minus 1 equals 0. And as a result of this, if you solve these three equations simultaneously, it would be a equals negative 1, b equals negative 1, and c equals negative 1. All right, I have ABC for pi 1, and I'm going to write pi 1 over here. Pi 1 would be rho to the power negative 1, v to the power negative 1, d to the power negative 1 times mu. And rearrange it would be mu rho v d. This also should be very familiar for you, right? Remember that you can write Reynolds number like this, rho v d divided by mu, right? So this is essentially 1 over Reynolds number, right? Now, so this was my pi 1, so I only had two pi terms, two-dimensional numbers. Now, based on my analysis, dimensional analysis, I know that whenever I'm doing the experiment in the lab, I just need to create a graph that has pi 1 and pi 2 on their axis, and then I don't need to do it for 1,000 experiment, or I don't know, 10,000 experiment. Whatever data that I get from my experiment is going to be on this curve, because I did dimensional analysis and I found the two important dimensionless numbers that are significant in this problem. So this was just an example, for a very simple example, that you only had two pi's, two dimensionless terms. I can do this example that you have multiple dimensionless numbers, or you only have one dimensionless number, right? So it's important to learn the process, the procedure, but not the example. Now the question that you have is, what if I select different repeating variables than you, than the other classmate that I have? Then what happens? So you remember that the repeating variables that we selected for our example were rho, v, and d, right? Why did we select all these repeating variables? Because they collectively had all three m, l, t dimensions. Now you can select any other combination of variables that have collectively have m, l, and t. For example, I'm going to do mu, v, and d. Again, if you go back to that slide that I showed you the dimensions, you'll see that these three will have m, l, and t collectively. All right, now, again, you go through the process and you write down your pi terms. So pi 1 would be, this time it would be mu times v times d, and pi 2 would be mu times v times d. But this would be times fd, and this would be times rho. Okay, and we have a, b, c, a, b, c. The same process. You go through the same process. I'm not going to obviously go through the process again. I'm going to show you that this time pi 1 is going to be fd over mu v d, and pi 2, if you do all the calculations in algebra, it's going to be rho v d over mu. All right, so obviously this time we are getting pi 1 equals g pi 2, meaning that pi 1 is a function of pi 2. So again, if you get a graph like this, and this is pi 1 and this is pi 2, you are going to get a different line from what you get last time, but both lines are correct. All the points are going to exactly fall exactly on this line. So it doesn't matter which variables that you select as your repeating variables, as long as they satisfy the criteria of having m, l, and t collectively. The line in this graph is different from the line. The equation of the line is different from the equation of the line that you got in previous slide. But your procedure is correct, and you can use either of them in the lab to generate this line. But you might ask, but which one do you prefer? We usually prefer those numbers that they have some physical manifestation before. So this pi 1 over here is different from what we got before. So I think it was pi 2 in previous slide. Let me, pi 2, if I can write on my screen, it's not working. There we go. Okay, pi 2 was fd, and if I remember correctly, it was rho velocity to the power 2 and d to the power 2. Yes, this was from previous slide, and we call this drag coefficient. Because this is a well-known, from previous slide, I should say, because this is a well-known dimensionless number, we obviously prefer to work with a well-known dimensionless number than some dimensionless number that is new to us and doesn't have any name. Okay, so both approaches are correct. No matter what repeating variables you choose, you're going to get correct answers. In this example, we have been asked to find a dimensionless number that can be established for a fluid flowing through the pipe using dimensional analysis. We already know that in pipe flow, the dimensional number that we have been using is Reynolds number, right? So we are going to use dimensional analysis to confirm that and to see that we have been using the correct dimensionless number. All right, we have been told that flow is a function of density. So this is variable number 1, viscosity, variable number 2, also velocity, variable number 3, and pipe diameter, variable number 4. Okay, now I'm going to take the steps that I showed you in my previous slide. Step number 1, if you remember, was define physical variables. The problem statement has already told us physical variables, 4 of those. So I can say that my n is equal to 4. We have 4 physical variables that describe the flow phenomenon. What's the flow phenomenon? Fluid flowing through the pipe. Now, next I need to define their dimensions. I recommend creating a table and writing down different physical variables and write down the dimensions in front of them. So I'm going to do the same. I'm going to start from density or rho, and then velocity. And I'm writing them in no specific order. You can write them however you want to. Diameter, I should spell it correctly. And what else? Viscosity. Okay, and then I'm going to write down their dimensions. Let me quickly create a table. So if this is the table that I'm going to use, viscosity is mu. This is dynamic viscosity. In the cell in front of it, I'm going to write down their dimension. To help you write the dimensions, it's always a good idea to write the units that you know for these, and then from the units go to dimensions. For example, the units for density in SI is kilograms per cubic meters. So the dimensions of that would be m, mass, divided by length to the power 3, right? You can do this for other basically variables as well. I'm just going to quickly write down them. After some years, I'm pretty familiar with how to write the dimensions, so I'm not going to write the units anymore. And then for dynamic viscosity, it would be m L to the power -1, T to the power -1. Perfect. Now, take a look at the dimensions of these variables. We have m term, mass term, we have L term or length term, and we have time term collectively in all of these, right? So you can say that because we have all three principal dimensions in this, m or small m would be 3, because we have mass, we have length, and we have time collectively in all of these. Now, since m is 3, remember that we can have n minus m pi numbers, which would be 4 minus 3 equals 1 pi terms. And this pi term is your dimensionless number. Perfect. Now, step number 2 was select the repeating variables. Okay, what I need to do is select m variables that have m, L, and T in them. Basically, they have the three principal dimensions in them. So I'm going to select rho, mu, and velocity. Take a look at the table. If you take a look at the dimensions of density, viscosity, and velocity, you will see that collectively, all three of these collectively have mass, length, and time dimensions in them. Okay. Of course, another choice could be mu, v, or d. This will also have all three principal dimensions in it. So you can either choose rho, mu, or v, or mu, v, or d. That's up to you. Okay, I'm going to actually go with my first option. All right, so selected variables are rho, mu, and v, and the remaining variable would be d, or diameter. Now we're going to talk about pi terms. What's the number of pi's that we're going to have? It's going to be equal to 1. How? Because n minus m is equal to 1, right? What I'm going to do is write the pi term. So pi term, we only have one, is rho to the power a, mu to the power b, and v to the power c times the remaining variable raised to the power 1, okay? Again, what I'm going to do is put the dimensions of different variables in this equation. It would be m, L to the power -3, everything to the power a, and then it would be m, L -1, T to the power -1, everything to the power b, and times L times T to the power -1, and all to the power c, times dimensions of d is L. All right, so let's do a little bit of algebra on this. It would be m to the power a, L to the power -3a, m to the power b, L to the power -b, T to the power -b. What else? L to the power c, T to the power -c times L. Don't need to write this, L. All right, so, and we already know that pi is a dimensionless number, so m to the power 0, l to the power 0, and t to the power 0, right? So what I'm going to do in next slide is do some algebra and write down the equation, basically find out the power of m, l, and t on the right-hand side of the equation, and solve the equation to find a, b, and c to find pi. Doing so requires you to combine the exponents of different pi terms. So what do I mean by that? First, you have mass term. To combine the exponent of different mass, we'll have a, b over here, and these are the only exponent of mass terms, so it would be a plus b. Now, next one is l, or length. What would be the exponents of l is negative 3a, negative l, and c, and then there is 1 over here, right? So it would be negative 3a, negative b, plus 3, plus 1. And then last principal component, principal dimension is t. For that, you have negative b over here and negative c, so it would be negative b, negative c, right? Now, again, because p has to be dimensionless, so the exponents of every single principal dimension should be equal to 0. So what happens if that is the case? So if this is to the power 0, and this is to the power 0, and this is to the power 0, then it would be 1, right? Which means dimensionless. And it is dimensionless, so what I'm going to do, I'm going to say that a plus b should be equal to 0, negative 3a minus b plus c plus 1 should be equal to 0, and then negative b minus c should be equal to 0 as well. From these equations, I can conclude that a is equal to negative b, and also b is equal to negative c, right? So putting all these together and solving all these equations, we'll have a is equal to 1, and then b would be equal to negative 1, and c is also equal to 1. Perfect. So do you still remember the original equation for dimensionless number pi? It was rho to the power a, mu to the power b, v to the power c, and d to the power 1. Let's replace the numbers a, b, c that we found. It would be rho nu to the power negative 1, and velocity to the power 1, and d. Now, if you write this number down, it would be rho v d divided by nu. This number should be very familiar for you, right? This number, as you already know, it is your Reynolds number. So now you understand that why we used Reynolds number in our pipe problems to find out the friction, right? So based on dimensional analysis, we confirmed that Reynolds number is the dimensionless number to be used in pipe flow problems.